Okay. Yeah. So I'll speak about dimension theory. It's some kind of companion to this previous story. Yeah. So again, we start with a smooth now projective variety. No funny semi-open varieties anymore, and we have an amp class. Yeah. So I recall that we have two operators, K and G. G is constant and grading operators, but K depends on parameters, and gives some operators on cohomology X and then we have this meromorphic connection on the trivial bundle on the plane with coordinate u. Okay, and we have isomandromic deformations as explained, and we restrict to algebraic cycles. And when we have point over some field like auxiliary, if you don't assume convergence, it will be some auxiliary piezo series. Then we get quantum spectrum, the spectrum of this operator K, and depends on parameter. Yeah, so the first observation, if X is Calabi-Yau or of general type, so canonical class is non-negative, then the spectrum consists of only one point, independent on the value of parameters of deformation. I assume X is connected. It's just by some grading reasons you see that the operator K will be nilpotent if you don't, or maybe constant if you add H0. Okay. Now, if you consider any variety, not necessarily of as before of ample canonical class, but restrict to Q equal to 0, then the spectrum again will be just one point, because the quantum product will be multiplication by say canonical class. It's an nilpotent operator, so the spectrum is 0. Okay, so, yeah, so when we deform parameters, the spectrum will move and decompose in smaller pieces. And if you generic point on this universal parameter space labeled by IMSA Ochoa group, you get maximal number of pieces. It will be elementary pieces. Yeah, but it's from this inaccessible conjecture about semi-orthogonal decomposition. But still, if you think about cohomology, maybe you put some coefficients here, extend scalars, you definitely get to decompositions in direct sum. Yeah, okay, so we get category or not category associated to each point of the spectrum, at least part of cohomology. And the goal will be to associate certain number, which I'll call the dimension of this point of the spectrum. And what are properties of these dimensions? It's kind of experimental story. It's not, there's no good reasons. First, at point Q equal to 0, when you get just a classical product, the spectrum consists only of one point, and the dimension should be this dimension of X, because this category is have only this elementary piece will be the whole category of coherent shifts on X. And the most important property is upper semi-continuity, which I expect. Namely, if you deform a little bit parameters in your base, this M algebraic, and then eigenvalue, if you deform a little bit, then eigenvalues can be split in some cluster of several, at least two eigenvalues. So you get, if it's really splits, then the new dimensions for new points will be no larger than dimension of the initial eigenvalue. So for example, if you start with a projective space, for Q equal to 0, the spectrum consists of one point, and dimension is the dimension of a projective space. But if you deform Q, then you get roots of 1, and all elementary components will be category of coherent shifts on a point, and dimension will be 0. So you go from dimensional projective space to many, many zeros. Yeah, and what will be this dimension? Yeah, if really there exists a semi-orthogonal decomposition of dB of coherent shifts corresponding to spectrum, and each component is indecomposable, not a direct sum of two proper subcategories, because accidentally one can make kind of two eigenvalues can collide without really talking to each other. Like two critical points, if like you have, for example, a function has some critical values and let's say isolated critical points, and then some critical values for two completely distinct critical points coincide. It's kind of accidental. We don't want to avoid it. Yeah, so it says that if it's indecomposable, then the dimension associated to the eigenvalue will be the third dimension of this category. Because for direct sum, yeah.
So a combination of these expected properties implies that any or maybe any reasonable semi-orthogonal component of dB of x has third dimension, which is less or equal than.
Yes, exactly. Yeah, yeah. That's the main point. Yeah.
And can you prove this?
I cannot prove because for this you need to say a reasonable semi-orthogonal decomposition. It's not any semi-orthogonal decomposition. Decomposition coming from Gromov-Witten invariants. It's a special class, and I don't have intrinsic description. What is it?
Okay, thanks.
Yeah. So I recall you what are third dimensions. Yeah, in fact, it was defined by many people, and it was by a very nice paper by Elagian and Lunds a year ago. Yeah. So the definition is very simple one. You start to iterate if you have a saturated category, like the category which appears in semi-orthogonal decompositions. Saturated has automatically third functor, as defined by Bondel and Kapranov. And then for categories coherent shifts and variety, it's a shift by canonical bundle and trees by canonical bundle and shift by dimension. So that's how dimension will appear. Now you iterate your third functor many times. Consider x in the category of functors like bimodules. It's well defined. And consider when you have each indices when you have non-interesting x's, you divide I by k, get a bunch of rational numbers, and go to limit. And then you get certain subset. It could be just closed subset, but theoretically it could be empty. But in examples which we have here, there seems to be always just one point, one number. Yeah, if you start from derived category of coherent shifts, you get exactly the usual dimension, which is non-negative integer number. And for fractional Calabi-Yau category, when the power of third functor is shifted by a certain number, the third dimension is the ratio n by k. This could be a non-integer number. And kind of the simplest example is Foucault-Seidel category of Landau-Ginzburg model when get just line. This context is potential x to power d. It should have at least critical points d at least 2, and this third dimension of this category is 1 minus 2 over d. This category also has some algebraic description, but yeah. Okay.
This is probably the quiver AD or AD plus 1, isn't it?
Yeah, I think so. Yeah. 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 Yes, it is. Yeah, it's quiver AD. In fact, yeah. Yeah, because I'm so used to symplectic geometry now, so AD is for me more complicated than varieties potential. Okay. Yeah, this story about third dimension, it's kind of bonus. And it's when we really have this very optimistic conjecture about semi-orthogonal decomposition. But even without it, as Sasha already noticed, it gives really very strong properties. And together with blow-up conjecture, which I discussed an hour ago, it implies the following criteria for non-rationality. Assume the dimension of things is at least 2. Okay, it's kind of stupid, but will not work in dimension 0 and 1 by obvious reasons. Yeah, if you have n-dimensional smooth projective variety and a generic parameter in modular space or algebraic, then we get kind of maximal semi-orthogonal decomposition morally or maximal spectrum. And if there exists a point in quantum spectrum of dimension strictly larger than n-2, then X is not rational. Why it is so? Because what does mean the variety is rational? You make blow-ups, and then it will coincide with, start with projective space and also start to make blow-ups. When you start with projective space, this spectrum consists of roots of 1 and dimensions are 0 for each pieces. And then you start to blow up. If it's in dimension n, you blow up at the center of dimension at most n-2. And then by the whole picture, which on previous talk, you get a spectrum will be union of spectrum of X and many copies of spectrum of Y. And because these things by semi-continuity will have dimension less than dimension n-2, you cannot get things of dimension n-2 at all. Yeah, so these things will really contradict rationality. And this criterion, it's kind of theoretical at the moment. It's really belongs to not exactly algebraic geometry, but really asymmetric algebraic geometry. It depends on the field of definition. It's kind of not sufficient to go algebraically closed field, because this even this notion of what is generic parameter depends on the field of definition, because this rational vector space, which I used from defining K algebraic X, depends on the field. I use only cycles defined from my base field. Yeah. So that's a criterion, and one can play with it. Yeah. So with Ludmil, last month we played a lot, and Ludmil will talk about examples. There are a huge amount of examples, and it's really amazing story that we compare with literature. It's kind of really 100% works 100%. If it's the all information, it really fits with all information from what people know in at least with this complete intersections and so on. So it really nails down this kind of basic question of algebraic geometry, but I'm really surprised by success of this criterion. Yeah, so what I will start with this just one numerical examples from which you can see.
Sorry, Maxim, can you say anything about stable rationality?
No, no idea at all. No, this thing really works for rationality, but not for stable rationality. It's some new ideas should be needed.
Thanks.
Okay. So yeah, you'll see Ludmil talks that will be some family of complete intersection from which you say that all of them are not, all smooth complete intersection of certain degrees are not rational, or very general not rational. Yeah, there are various situations. Yeah, this criterion really works. Okay, so I'll start with kind of example which quite simple. You consider equation of degree 3 in 5 homogeneous variables. So it will be 3-dimensional cubic in P4. So as a Kähler class, you get ample class, you get ample line bundle or 1. And we set all other parameters, all this deformation parameters to 0. So we get just only Q for quantum product. And then one can easily, it's Fano variety, one can easily calculate K and G, get only finitely, actually curves of degree 0, 1, and 2, which contributes to all calculations. And in cohomology of X, you have even dimensional, even degree cohomology, which is 4-dimensional space, like H0, H2, H4, H6, restriction of cohomology class of projective space, and something H3, we get some intermediate Jacobian, which I ignore. It will be odd part. Yeah, so we get this basis of even part. It's 4-dimensional space. And operator K is dependent on Q. It's actually not series, it will be polynomial because in Fano case. So you get this matrix, which is not exactly upper triangular because you get product by, I think it's Fano of index 2. So this anticanonical class is 2 times line hyperplane section. Get 2 in front. So it will be multiplication by line bundle and 2 correction coming from curves of degree 1 and 2. Yeah, it's actually very typical if you consider complete intersection in projective space or weighted projective space and get quantum product by O1 or multiple of O1, you get similar picture. You get kind of diagonals multiplied by some power, larger and larger powers of Q. And gradient operators, it's by normalization, it's it will be half integers. Okay, so we get this. I think you get this differential equations, which we one study and isomorphism deformation, and we study actually behavior only at near zero. And near zero, what will be solutions? Yeah, first of all, if Q is non-zero, it's actual number. Then you get 2 solutions which have exponential growth. But it will be really pure exponent, no monomial of U. And will be 2 solutions. It will be kind of vector valued function, but consider growth over norm. One solution grows with U2 minus 1, 6, and another U2 minus 5 over 6. Okay. And if you put Q equals 0, get just classical product, then solutions will be U minus 3/2 multiplied by logarithm or square logarithm cube of logarithm. Yeah, and you consider, yeah, if you ignore this pure exponential factors, looks what is the growth. It's actually quite different. So for Q not equals 0, you get U to power 0 twice, and U to power minus 6 and 5 over 6. And for Q equals 0, you get minus 3/2, and I kind of highlighted by red only the last one because it's the most singular kind of. When U is very small, it is the largest number. Okay, so you see this number 3/2 and 5 over 6 with minus sign. What are them? 3/2, it's minus half of 3, yeah? And what is 3? 3 is dimension of my variety. Yeah, that's pretty obvious. And what's 5 over 6? 5, 6, it's minus half of 5 over 3. In 5 over 3, it's dimension of kind of interesting part in semi-orthogonal decomposition of this Fano variety. Namely, it has the semi-orthogonal decomposition in 3 pieces, or category determined by O, it's exceptional object, another exceptional object O1, and the third piece is some fractional Calabi-Yau, which also will be responsible for odd degree homology of X, and it will be Calabi-Yau category of dimension 5 over 3. Yeah. So this examples actually tells you everything, and that leads me to the following kind of proposal: definition of dimension with the growth of solutions. So suppose I had some point on my parameter space. I take some eigenvalues, which is Zi, and the conjecture is that the dimension of third dimension of category corresponding to this each eigenvalues, it's minus 2 times the minimal number S, which will be non-positive rational number, such as this solution which glows like exponential terms, exponent Zi over U. It comes from this eigenvalue of operator K. Then U to power S and maybe some power of logarithm, which I ignore. Probably
Maxim.
Yes.
So does it mean in particular that the upper third dimension equals the lower third dimension for these categories?
No, I think for this categories, this upper equal third dimension is equal to its third dimension just one number. It's not an interval.
So it's another special property of these subcategories. Right?
Yes, yes, yeah. Not like for like representation of some acyclic pure when this third dimension is actually the whole interval, if it's wild pure. Yeah. Okay. What is the evidence for this formula? If X is a Fano complete intersection of hypersurfaces of certain degrees, some degrees should be less than n+1 in order to be Fano. Then the semi-orthogonal decomposition we kind of know by Sasha Kuznetsov. It's you take just bunch of powers of ample line bundles, and then the rest the maximal possible, so that will be form a still will be no Holmes in wrong directions, and the rest it's Kuznetsov component. It seems to be in general kind of indecomposable, and so d sum is the sum over all numbers di, and the spectrum is 0 and maybe rescaled roots of 1. It's not exactly roots of 1, but it could be rescaled by some number. And this predicted third dimension is the following. One can write formulas in kind of pure numerical terms. You get this number n, di, take sum, that maximum, take some quotient. But there is actually one can understand almost everything is formal geometrically. It's dimension of manifold x minus 2 times Fano index of x. So it means that anticanonical bundles should be some power of line bundles will be divisible by some number in Picard group, and divide by d max, maximum of this number d, which doesn't have any geometric interpretation, but that's the formula.
Maxim,
yeah.
So, for instance, if you consider intersection of a quadric and a cubic in P5,
yeah,
then your formula gives just one line bundle, right? But
yeah.
in this case, the orthogonal complement is not indecomposable.
Yes, yeah. If it's even, it's not indecomposable. I just consider this orthogonal complement.
Yeah, but what I want to say is that the formula for the dimension that you write is more likely to be true for a piece of this orthogonal complement.
No. I think it's for the whole story. If again in small dimensions you get some exceptional situations when this Kuznetsov component wants to be still decomposed. But if I do not decompose it, I claim that its third dimension will be exactly this number without any exceptions.
So what do you mean by saying that you claim this is true? Do you have a proof or what?
It's called.
Or do you have some evidence?
I have some evidence, yeah.
And what about proof?
I don't have proof. Yeah, okay, yes, it's
okay.
a different type of talk. Okay.
Yeah, sure.
Okay. Yeah. Why actually it's true? Yeah, there are many reasons to believe in it. Yeah, no, at least, yeah, strictly speaking, it's just definition of some number. I don't really know rigorously it's a third dimension, but so in next formulas, you just treat this dim-ser, it's exactly this form, what I given by this formula. And what one can check, which is really non-trivial, check on a computer, hundreds of cases, is that you get some rational number, yeah, which will be this would to be a third dimension of this category, associated to critical value 0. Now I'm interested in a kind of integer part of the story, maybe not exactly integer part, interested in integer number, which is less than equals this would to be third dimension, which has the same parity as the dimension of my manifold x, should be even or odd number depending on parity of dimension x. You get certain integer number. And this integer number turns out to be the maximal number k, such that Hochschild homology group for my category if the index k is non-zero. Yeah, that's I'll speak about in terms of invariance of triangulated categories, but this has a meaning in terms of Hodge structures. It's maximal values of difference of indices PQ or QP in the Hodge decomposition of cohomology of X. Yeah, so this things, because X is complete intersections, you get either algebraic classes coming from projective varieties or some primitive cohomology in the middle degree. So it means that Q minus P has the same parity as dimension of X. And in general, if you get any projective varieties, then you get upper bound that the dimension of your manifold is greater than or equal to this integer number. It has the same parity. And what happens here, we know kind of parity a priori, but dimension is rational number. And this Hodge width, it's the maximal possible with given parity and upper bound by rational number. Yeah, so it's looks very nice. Yeah. So for example, there are cases when this category is really category of coherent shifts of some variety. Then this dimension will be integer, and then you get equality. And there are cases when this category is fractional Calabi-Yau, then you get fractional Calabi-Yau dimension. Yeah, so it's all fits very nicely. And also this works not only for complete intersection projective space, but in what's called well-formed complete intersection weighted projective spaces. So you get some complete intersection which are automatically smooth. They do not touch ramification locus of the weight projective space. And the formula is kind of similar. The third dimension seems to be the dimension of X. And now you take a rational number, sum of weights for projective space. As the sum, it's again, I think, index of Calabi-Yau divided by Dmax. So it's essentially the same formula. And what is the main tool for this complete well-formed complete intersection weight projective space? At least for when consider quantum product on part of cohomology which came from the restriction from the ambient weighted projective space. Everything is known, and there is essentially from kind of the first work by Sasha Giventhal in what it was 1997. Yeah, when he proved mirror symmetry for quintic threefold first time. Yeah, so there's some hypergeometric equations. People generalize it. And then from these hypergeometric equations, one can really understand the maximal growth of solutions. It's pretty straightforward and get exactly this formula. Yeah, so this expression, it's something comes from some hypergeometric equation, which probably Ludmila will talk about.
Maxim,
yeah.
Do you have a similar formula for other toric varieties? I mean, for complete intersection?
No. I think it's feasible, but I don't know. Yeah, it should be feasible for general toric situation. I just didn't.
But what is it going to compute for general toric varieties? What kind of semi-orthogonal decomposition you are going to consider?
Yeah, this equation, because there are many categories around. Yeah, there's really not one good. Yeah, that's actually it's a good question, because we don't really know how to label the eigenvalues of this operator K in general situation.
And can you compute them at least?
No, it's really a complicated story. I think even Grassmannians is already interesting, very non-trivial story.
Yeah, but Grassmannians are not toric, right?
No, but okay, it doesn't really matter. Yeah, I don't know.
Okay.
I have to say. Okay.
Thanks.
Yeah, no, really. Stop. We play with this weighted projective space complete intersections. It's already a lot of examples here. Yeah, so there is something. It's a bit hypothetical. it's related to some one early results in Gromfitton theory, some called Reconstruction Theorem. Yeah. So what goes on if we have some, let's say, even Fano variety? Yeah, my story is very general, not for Fano variety, but Fano variety is its main playground. Then the meromorphic connections, which we write here, this kind of two matrices. It's nice, it's algebraic geometric or non-explicitly only for very special values of parameters, namely when all these parameters t a equal to 0, except this stupid word which you can h0, which corresponds to shift, and again h2, which you can tread with this q variable q. Yeah, so you don't deform by h4, roughly speaking. Yeah, so that's something which is known explicitly, and when deform, we get some kind of not terribly explicit things, which has solutions to some equations which we don't know what's going on. And yeah, so it's this equation. If you deform this parameters in Frobenius manifold by class for h4, h6, and so on, whether you get additional splitting eigenvalues with respect to situations you know kind of algebraic geometrically or not, it's not clear at all. And what I expect if h even, or maybe just algebraic part of x, is generated as a ring with a classical multiplication by h2, then there will be no additional splitting. Like in this previous example, I just wrote we get a lot of one-dimensional parts of cohomology truths of 1 and some high-dimensional piece at 0, and I claim if we deform by h4 and 6, it will be still high dimensions, will not split anymore. And what is the reason for this? It's a reconstruction theorem. It's one of result of my old paper with Yuri Manin. So if h even is generated by h2 or rational numbers as a ring, then all genus 0 Gromfitton invariants restricted to h even are uniquely determined by the quantum product deformed only in h2 direction in second cohomology. So it means that you consider quantum products with h2, and by divisor axioms, it just count what is the degree of things. So what you really need, you need modulus space of genus 0 curve with 2 mark points, no more. And so you get some, you get certain cohomology classes in the square of your variety, and also you get classical product in cohomology. And from this bunch of classes, which could be infinite. For example, for quintic threefold, you need curves of all genera, of all degrees. But it's really much simple information. There's really no infinite series. It maybe you get like series in variables corresponding to h2 with values in matrices. And
Maxim,
that's it. Yeah.
I think that there are examples of varieties for which small quantum cohomology is not generically semi-simple, but big quantum cohomology is. And the simplest such example is the isotropic Grassmannian of two-dimensional subspaces in a six-dimensional vector space with a symplectic form.
Yeah. You mean small if you deform by h2 and by h4 you get.
Yeah.
Yeah, then it will be probably, yeah, then probably I'm wrong. Yeah, because what I said that this to know all this, there's no all complicated things at h4. It's all information already hidden when you deform by h2. Yeah, it's pure algebraic question from this reconstruction theorem to see whether these eigenvalues appear or not. Yeah. So it's essentially a question about metrics valued series in several variables. Nothing else. And the quantum product and the classical product. Yeah, so certain interaction of this stuff. Yeah. Yeah. No, it's kind of really wild short. I'm not sure that it's a good explanation, but at least it shows that in such situation one kind of can analyze these things through kind of more manageable data. Yeah, so the next things I want to describe, it's kind of perspective point of view of Landau-Ginzburg models, mirror duals, which when they exist. Yeah, so what is why I believe the semi-continuity and of all this, I think the picture is the following. So imagine kind of that we have mirror dual, and in general, I consider the following situation. I have a maybe non-compact complex manifold, maybe non-algebraic one of some dimension, and a holomorphic map to C. And I assume that the critical locus is have a critical locus, closed analytic subspace, maybe with nilpotence. And I assume the following. The first thing is this critical locus is compact. And then I assume that there exists a metric on why it's only existence, isn't it? Not a choice. And actually, I'll assume that critical locus is non-empty and connected, and the critical value is 0. It's only one critical value because it's connected. Yeah. And so the third point can be really achieved very easily if you have compactness. You just replace your critical locus by tubular neighborhood of connected component and shift by constant to make critical value 0. Yeah, so yeah, the whole thing's really, this whole variety is really plays no real role. It's you need only a germ of variety in your critical locus. Yeah, so so if you get such a situation, then one can consider Z-graded complex, namely consider on this open variety Y, C infinity forms, and the differential will sum of 3 also add formal variable U, and the differential will be sum of 3 terms, d bar, U times D, and D times W, and it's calculate hypercohomology of Y with its coefficients is the sheaf of holomorphic forms and series in U just by d bar resolution. And if you have in this complex closed chain, and I assume that's not a form power series but actual convergence, germ of convergence series in variable U with various forms, then the property that it's a closed chain means that if you rescale a little bit, you apply U to grading operator, P minus P components and multiply your exponent, you get closed form. Yeah, so it's essentially closed form, and we can approximate to integrate with a pair when with respect to vanishing cycles and get things like this. So one can formulate a very general conjecture that in such situations, the cohomology of this D total of form power is a free finite rank module of a Taylor series in variable U. Yeah, U is the same U which was before. Yeah, if Y can be embedded in some algebraic variety and function will be a polynomial function, then everything is okay by irregular Horst theory. But in principle, I think it's a really nice question in kind of complex geometry, scalar geometry, this degeneration. Yeah, yeah, that's kind of Landau-Ginzburg model. And if you want Landau-Ginzburg model mirror to actual variety, these things should be Z-graded. Foucault-Seidel category should be Z-graded, and for that we need to assume that variety has a holomorphic volume form, not vanishing everywhere. And what I claim that in such situation, before going on, I just forgot to say that in this conjecture, you get vector bundle on over formal line in variable u, and because you interpret as a closed forms and can integrate with respect to vanishing cycles, it means that you get a flat connection, and this flat connection will have second order poles equal to 0, so you get a situation in which one can speak about growth of solutions even in formal sense, because one can write solutions using level to routine decompositions. It will be exponents multiplied by some fractional powers, and the whole thing makes sense. Yeah, and when you get such a situation, when the critical locus is connected to non-empty, when it was one of kind of technical assumption, I claim in this case you get canonical natural one-dimensional subspace at fiber 0. It actually gets splitting at fiber 0 of my bundle will split in some of canonical non-trivial one-dimensional space and something else. And what is this? What's the origin of the splitting? When consider fiber of 0, you'll be hyper. I just recall you because consider form power series in U, and this differential U times D plus dW, and when you equal to 0, this U times D disappears. You get multiplication by differential of my potential. So what I had hypercohomology of Y with coefficients and forms with differential multiplication by dW. Definitely volume element is still my multiplication by one form because it's top degree form. So it's a class in this hypercohomology. But when consider this hypercohomology, its cohomology of Y with coefficients is complex of bundles. You can restrict to critical locus. And on critical locus, this differential will be 0, because by definition, critical locus when differential dW is equal to 0. So you get just direct sum of cohomology of critical locus with restriction of this bundle to critical locus. And nth cohomology contains H0 of critical locus reduced with coefficients in n forms, because now we have volume element also trivialize these things. You get identified with O, because it's connected, you get one-dimensional space, it's C. And if you go calculate the whole composition, you see that the volume elements goes to 1, so you see that you get really splitting. It's a subspace and a quotient space, so you get direct sum. And the conjecture, again, studying simple examples like isolated singularities, is that the leading growth of solutions appears in exactly one-dimensional subspace in cohomology of D total, and so you get some kind of subbundle, rank 1 subbundle when you get this maximal growth, and its reduction to equal to 0 will be exactly this one-dimensional space. Yeah, so it's so you see that it's kind of analog of what? If you because this growth thinks roughly like weight filtration in cohomology, and if you consider cohomology of variety, there is of connected varieties, there is some specific one-dimensional space H0. It has minimal possible weight 0. All the rest has larger weight. So it's analog of this distinguished one-dimensional subspace. And this upper semi-continuity, one can relate to something called stingering spectrum. Or for isolated singularities is Arnold spectrum for singularities. And there was Arnold actually conjectures very long time ago some semi-continuity. You start for like singularity x cube, and then you get with my normalization you get maybe 1/3 as a dimension or whatever minus exponent of the maximally singular solution. And then if you deform it, we get quadratic singularity, you get 0. So 1/3 is bigger than 0. So you get always this upper semi-continuity. This singularity became simpler if you deform them, and they split into simpler pieces. Yeah, so Varchenko proved it, and the proof was pretty tricky using some resolution singularity, the mixed hot structure, and Steenberg proof for non-isolated singularity. I don't think it's optimal proof. We should really find a better proof. that should be with the growth of solution. It should be some kind of direct proof, which still eludes us. But my feeling is the story is really not finished even on the basic question. Yeah, so we get this upper semi-continuity, but this upper semi-continuity, it's for deforming pairs of variety Y and potential W. Yeah, it's actually, you get some deformations, but if it's really mirror to some Fano varieties, you get not so many deformation. You don't get this corresponding deformation for this in quantum products only along H2, maybe H0, and that's it. You don't really deform along H4 and H6. And what roughly correspond, you can consider deformation theory of this guy, variety with potential. You get polyvector fields and make d-bar resolution, get d-bar forms as well as in polyvector fields with proper differentials. And Calabiot you identify with this cohomology which you play with. And then usual deformation will be like Beltrami differentials, 0-1 forms as well as in vector fields. But now we're interested in 0-2 forms as well as B vector fields and so on. Yeah, it's not terribly clear what is going on. It will be not geometric objects, and what is the critical values. It's more tricky notion one can extract, and yeah, and the whole things became kind of semi-continuity. It's even less clear. There's no proof because we go beyond algebraic geometry with these deformations. Yeah, when Varchenko consider isolating singularities, fortunately, it's sufficient to get Milnor-Rabo. You can really just deform potential W.
But what did you look at the exponential integrals?
And he also looked for exponential integrals for isolated singularities. Yeah, it was and this number which maximal growth also appears in his story.
But is it encoded in the intersection of the Lagrangian corresponding to this deformed graph of dW with zero section?
Yeah, no, if it's more singularity, you get only zeros. All dimensions will be zeros. But if it's not more singularity, you get larger numbers. Yeah, but it's, yeah, no, I was hoping it could be made in some kind of like Mativik integrals, calculation of some volumes, but it's still eluding. Yeah, I don't know. Yeah, but at least there are very good class of semi-continuity which is already exists in literature for many decades. Yeah, this semi-continuity, it's a really central question, and what we really need only in the case when we form classical product just to make application to birational geometry, we need not very general theory, but very special theory. And what is this very special theory? It will be kind of minimal conjecture. I want to formulate it in the following way. Suppose you have matrices of some size. Size will be dimension of even not cohomology of some variety at the end of the day. And I have a grading operator with respect of integers, semi-simple operator, like this bold G before. And I have two form power series with values in matrices satisfying these two equations. One can expand and get infinite series of equations, and yeah, it's reduced to some kind of scheme of infinite type with infinitely many things. Yeah, so we can get this infinite dimensional variety, and in plain terms, it means that we get flat connection in two variables in T and U. It is meromorphic flat connection. Okay, just let variable T equal to 0. And you get a connection in U which we like to play with. It will be like classical limit. And then you get generic connection over a Lorentz series, over field of Lorentz series in variable T. Just all K and G interpret as not Taylor series, but Lorentz series. So we again over field. Yeah, and assume K0 is nilpotent. It's really our point of interest because we are starting with kind of classical product with canonical bundle. And the special connection has regular singularity. One can be even more specific. Let's say that K0, maybe it's fine here. K0 just raise grading exactly by 1. Then the generic connection of a field of Lorentz series is of exponential type. So it means that it's over any field of criterion 0 and have some level to routine classification of connection of form power series. And in Lorentz series in variable u. And then there should be some of terms which could be exponential, could be something wrong, could be exponent 1 over square root of u. And we want to avoid it, so it's exponential type. And then if consider, let's say, a solution without exponential term, and consider the largest possible growth, and consider exponent of the growth, then should be the exponent, should be some number, should be kind of more negative numbers than those for the general connection. For general connection, you get more mild singularities. Yeah, and if you try to understand it, it seems that something is fishy here. We cannot even formulate this singular generality because the largest growth exponent, if you have base field, which is not C but something else, Lorentz series, it's an element of its algebraic closure. So it's Puiseux series. So how one can say that one complex number is bigger than Puiseux series? It makes no sense. But what I expect is that this largest growth exponent for generic connection, it's actually, again, complex number inside this Puiseux series. And how to compare what does it mean one complex number is larger than another? There's a difference is a rational number. And for rational number, one can see it's positive or negative kind of a priori. So it's notion invariant under orthomorphism of field of complex numbers. So it will be the exact meaning of this story. So this exponent for this regular solution for it general connection are numbers, elements of Lorentz series which differ from our complex numbers by rational numbers and then get certain inequality. Yeah, so that's a precise formulation. Again, it's far from being theorem, but one can check some examples. It seems to work. Yeah, and this will be certain basic property about equations to prove, which much simpler than kind of more ambitious conjectures you can formulate, and that will be sufficient with together with below formula for rationality equations. Okay, thank you.
All right. Let's thank Maxim for the nice talks. More questions?
So your last conjecture, it has nothing to do with geometry. It's just
nothing. Yeah. Eventually, yeah. It's
about differential equations.
About differential equations. Yeah, and the size of mononomic deformations. Yeah, exactly.
But does it have some geometric implications?
Yeah, together with blow-up conjecture, it will lead this whole criteria for non-rationality.
But it applies for other equations as well. I mean, so
I don't know.
Yeah, because it's about differential equations, it applies to other equations.
Yeah, it's maybe we will be yeah. There are journals.
But it's strange that you could not prove it. I mean, it's kind of,
no, I didn't try hard. I didn't try hard. There are many things to try here. I'm not sure that it's very complicated.
Hey, yeah, I have a question.
Yeah.
In this, you have this asymptotics that has some exponent of growth, but you also had a factor of log u, which had its own exponents.
Yes.
Does that exponential factor have any significance geometrically?
Powers of log.
Yes.
It's something u. One can wonder what does it mean. I have no idea.
Okay.
So Maxim's more traditional approach to rationality, let's say on threefolds, is to look at the geometry of spaces of rational curves of growing degrees.
Yeah.
So I'm just wondering, so you're looking at Gromov-Witten invariants as like numerical invariants, but maybe something about the geometry of the space of rational curves.
Could be, yeah.
It's kind of connected to your, well, that's fantasy.
Your
asymptotic expansions.
Yeah, I have no idea. Yeah.
Yuran, these numbers indeed can be read in some cases from these curves on the variety. That is true. So I've looked at some examples.
Yeah.
But you are correct, yes.
Yeah.
Other questions?
Yeah, I have one other question. Is there any hope of, if I pick a critical value and a Gabrielov path, is there any hope of actually reconstructing from that data somehow the semi-orthogonal component? Like it's a subcategory of things with a certain stability?
Yeah, no, what kind of one can dream if you have semi-orthogonal decompositions, get projector functors to semi-orthogonal decompositions, yeah? And then projector functions given by some kernels. The kernels will be some complex of shifts on square of your variety. And what we use some kind of curves, rational curves with 2 points, more or less, yeah? And some virtual fundamental classes. Yeah, so one can kind of try to relate virtual fundamental class to these kernels. Yeah.
Okay, thanks.
Maybe comment to Ben's question. If you think pure abstractly, again, if you do this Fourier transform of your quantum equation and look for the perverse Schober, if you can do it, then you can make the Fourier transform of the perverse Schober, and it will automatically comes with.
Gives a category, yeah.
No. It's not just the category, but semi-orthogonal decomposition.
Semi-orthogonal decomposition, yes, but
right. That makes sense to me. Thanks.
Yeah, at the moment it's completely mystery. The whole this categorical picture. Yeah.
Maxim.
Yeah.
Other questions?
Can you give more details about relation of the kernel of the projection functors to some virtual classes?
Yeah. Yeah. It's at the end of the day we use this quantum multiplication. So we use curves with two special mark points, and there are other mark points. When you put these corrections, I really have no idea what is going on. Because you, in order to describe spectrum, we really use infinitely many information curves of larger and larger degrees. But it's somehow at the end you have to boil down to some kind of algebraic expression, not infinite sum. No, it's really baffling, the whole story. I have no idea.
Thanks.
All right, so if there are no other questions, let's thank Maxim again.
Okay.
And so we will resume at 1 p.m. Eastern Standard Time with a talk by Tony. See you in